Experiment 4 is molecular models in stereochemistry. The objectives are to build models using ChemDraw to calculate bond distances, bond angles, and dihedral angles, to visualize organic molecules in 3D using Chem 3D software, and to determine stereochemistry of chiral carbons in a molecule. Molecules can be built either in ChemDraw Pro or directly on Chem 3D. Template structures are available and should be drawn first before calculations can be performed. Part A is using ChemDraw to build molecules. We are going to draw tert-butyl cyclohexane. The software is in a package called Chem Office. So if I click on the pull down menu, there are two softwares. One is Chem 3D, it's version 2019, and then the other one is ChemDraw 19.0. So I click on ChemDraw and it takes a while to load it. Finally, I got this white panel. On the left side is the toolbar. These are actually templates. And at the very bottom is a cyclohexane chair structure. So I click on it and I click on this white panel. Then we're ready to build the molecule, which is tert-butyl cyclohexane. And then I'm going to attach tert-butyl substituent. So I'm going to use this bond, click on it, and then I'm going to attach it equatorial in this carbon here. Then attach one more methyl, another methyl, another methyl. So that's our tert-butyl cyclohexane. And now if I click on the lasso, it will actually encircle it, or I can also encircle it. And then I right click and then I copy. And then I'm now going to open Chem 3D Bio or Chem Bio 3D. And I go back and then I click on the software and it will open up for me the other software. It's called Chem 3D or Chem 3D Ultra. So now I have a blue screen. And now I'm going to attach by doing edit and then paste. So now I have the molecule. So I also have it here. So I can also actually draw it here. This is now the tert-butyl substituent and I have the cyclohexane. So now I can use the tools on top. So I can use the hand and then translate it like that. Or I can use this tool to rotate. So I can rotate like this. Okay. So I want to orient the molecule such that it's the same as the picture that I've shown you, that I've drawn in the handout. And then I can also click on View, and then Model, Display, and then Display Mode. I can also change the model into sticks, and then rotate the molecule. Okay, so now you can see. So I have a chair. This is the chair. And then I have equatorial, axial, 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 equatorial. This is the tert-butyl substituent, and then you can see the H's, up, down, up. So down, up, at the back, down, up, equatorial, up, down, up, and then down, and then up, down. We are now going to measure the bond distance between this carbon and then this carbon, which is labeled as carbons 1 and 2 in the drawing in the handout. So if I click on this carbon, it will show as C5, and then this carbon as C7. This numbering is arbitrary, and actually if I hover the mouse on this carbon to carbon bond, it will tell me the distance or the length as 1.523 angstrom. So that is the bond length. The other way is to go to the structure tab. So there's a structure tab, click on it, and then measurements, and then generate all bond lengths. I click on it, and then it's because this carbon is labeled in this drawing, is generated by the software as C5 and C7, I can locate that bond distance. So at the bottom is C5 to C7, and if I check it and then I highlight the C5 to C7, it will show me the distance as 1.5 angstrom, and the actual length up to 3 decimal place actually is 1.523. So write this down please in the first blank. 1A, the distance between C1 and C2 in the handout, although in this drawing is C5 to C7, is the same. That numbering here is arbitrary. So the bond length is 1.523 angstrom. Again, the bond length is 1.523 angstrom. So this is a table on the left side. And you can actually also determine, for example, so this carbon is C10 and this H is C28. So you can locate that C10 and C28, which is number 3 in this table, and then it will determine for you that distance, which is 1.1 angstrom. So this table calculates everything in this molecule, carbon to carbon bond, carbon to H bond. And then also on the right panel here is also a drawing, and you can also draw the molecule in here instead of drawing it in the ChemDraw. So either way. So now we're gonna do letter B, which is measure the bond angle of carbon 1, 2, and 3. So if I now do again structure, measurements, and then generate all bond angles, and then I have all the data on my left side. So if I now want to rotate it so that I can see better, so I'm trying to measure the bond angle between carbon 5, 7, and 10. So again, the number is arbitrary. The one in the handout is C1, C2, C3. So this is the bond on this carbon and the cyclohexane, and then on the third butyl, this carbon and any carbon here of the methyl. So now if I highlight this, okay, so I highlighted this carbon. This is the cyclohexane carbon, which is this carbon over here. And now if I want to measure the bond angles, I will do again the structure tab and then measurements, and then I do generate all bond angles. So I have everything in here. So if I want to do this, I have actually C5, all right, and then this is C7, and then this is C10. So I go back here. So this carbon is C5, C7, and then C10. So we're going to look for that carbon. So measurements. So it's this one here. So if I highlight it, it's now measuring this angle. So this is the angle. So write that down, please, on letter B. It's 109.462 or 1.9.5. So we know that angle. So it's showing you this angle that we want is 109.5. So that is that angle of C1, C2, C3 in the handout. So you can generate all the other information. Say I go back to measurement. Say I want this one. So what is that? So I can highlight it and it will locate for me in the structure the angle. Okay, so in fact it's this part here. So it's this H, carbon H, again it's 109.5. Okay, so everything is calculated in here. So it's a table. Letter C is now measuring a dihedral angle and then draw the molecule with the dihedral angle. So in this model or in this structure, there are so many dihedral angles, but we're gonna pick one, which is this part in here. And if I rotate it, if I put it at an angle that you can see, so we want to measure this dihedral angle over here. So the dihedral angle can be negative depending on how it's measured. And also dihedral angle is the angle between two planes. So this is the definition of a dihedral angle, is the angle between two planes. So you're intersecting two planes. As opposed to a regular bond angle, the bond angle is typically two lines intersecting. However, for a dihedral angle is the intersection of two planes. So if I put down the molecule like this, you can see that it's in fact the dihedral angle is composed of three lines. This is one line, 2, and 3. So this is 1, 2, and 3, as opposed to a bond angle is just 1, 2 lines. So that's a bond angle. Dihedral angle would be 2 planes or 3 lines or 3 bonds. So 3 bonds would be 1, 2, and 3 behind. So in a Newman projection, this is the back carbon contains the H. So you can clearly see that it's about 60. So now if you do again structure tab and then measurements, generate all dihedral angles. So there's so many dihedral angles. So if I hover the mouse on here, it's H14 and then this is C2. And then if I put it a little bit down, that's C3, and then this is H15. So just write that down, please. So we are determining the dihedral angle composed of this plane and the plane behind, this angle. But it's not really a bond angle because you have 3 bonds. So one bond coming from H14 to C2, and then C2 to C3 behind, and then C3 to H15. So you have 3 bonds as opposed to 2 bonds like this one, H14 bonded to C2 and then H13, that's a bond angle. So we're now doing dihedral angle, which is this one, composed of 2 planes, one plane, the second plane. So now if you go back to the measurement, you look at H14 bonded to C2, bonded to C3 behind, and then H15. So now to the measurement, okay, I highlighted it here. Okay, so now if I click check, that's gonna be our dihedral angle. So now draw it. Okay, so I'm gonna put it a little bit down, or like that, and then now it's measuring as minus 66.5 or close to minus 60, or the way why it's negative is measuring it actually the opposite direction, but it's 60. So now this is the in the structure. Okay, this is in fact this carbon over here, and then it's the foot of the chair. So the back of the chair is here, and then this is the foot of the chair shown in the drawing. So if I go back to my drawing, it's that carbon here, which is C2 over here. So therefore, now you can draw it. This is like a Newman projection. So just draw this part over here, and then you put a line that this is the dihedral angle, which is 60, or in this case, it's actually minus 66.5, which is generated by the computer. You don't have to write everything, so just do a squiggly line, squiggly line. It's like you're cutting it because you're only interested in this part here, which I showed in yellow. So just cut it like that, squiggly line, and you're drawing this part because that's the one that we're interested in which we're trying to determine or measure a dihedral angle, and then draw the molecule with the dihedral angle. So this is the foot, or this carbon is this carbon over here. Okay, so it's slightly twisted so that the back, which is C3, is a little bit more towards the back of the C2. So the structure the structure drawn is something like that. Okay, so this is the bottom and this is the top. Okay, you see that this is this carbon, and we're measuring the back over here. So that's one bond. This is C2, C3 in the model over here. Okay, so now we're done with the first page, which is part A. Part B is using ChemDraw to determine stereochemistry of a molecule. The molecule below is limonene. So we are going to draw the structure again in ChemDraw. So we are going to delete 3-butyl cyclohexane, delete, and then we are now going to build the molecule using cyclohexane, and then we are going to put a double bond. So we are going to put a bond by clicking solid bond, and then attach a bond up, and then the bottom one we are going to use this hashed wedge bond, and then there is a methyl attached, and then a double bond. So again, we are going to transfer this picture or this image in Chem 3D. So we are going to clear this. So we are going to transfer this drawing into Chem 3D. Paste. And now we have the molecule also shown on the right side. So notice that if I have the double bond, so the double bond is this, so it said alkene. Okay, so this is to the back, so the H is towards you. So if I rotate this, so look at this structure on the right. If I rotate this molecule or kind of flip it like a hamburger kind of thing, so I will rotate, and it's gonna look like this on the right. Okay. All right, so we're gonna go back to that previous model, and we are now going to measure the bond distance with correct units and then bond angle. So as shown in the handout, we are going to measure the double bond C1 to C2. However, it's labeled here as C5 and C6. So the distance, I can actually just hover my mouse on it. So it's 1.341 angstrom. So you can write it on that blank. It's 1.341 angstrom. And again, the other way is to do structure and then measurements and then generate all bond lengths. So we are going to look for C6 and then to C5. So C6 to C5 is this. So it's now yellow. And then again, there is the measured or the actual distance, which is 1.341 angstrom. So that's the highlighted in yellow. So the bond angle in the handout is going to be this carbon. So C1, C2, and C9. Okay. So we're now measuring the bond angle of this carbon, labeled here as C5, to C6, and then to C7. So it's C5, so C5, 6, 7 is the one labeled in the in this model. So we can go back to structure tab and then measurements and then generate all bond angles, and now you have it here. Okay, so it labeled the distance, but the angle, so we are looking for C5, 6, and 7. So this is the angle here. So if I check it, now it's measuring as 118 or 120.4. So go back to the measurement. So I checked this. Okay, so it's 118.4. So, or close to 120. So write it down, please, in letter B, blank, part B. So 118.4 degrees. Letter C is now measuring the bond angle labeled in the handout as C7, C8 to H8. In this case, it's actually so it's this carbon here. Okay, so it's carbon number 8, 10, and then H26. So if I hover the mouse, it's going to be carbon 8 to carbon 10, and then the other bond is H26. So we have two lines intersecting this line to form an angle. So now if we do go back to this measurement, so we're looking for H26, C10, and C8. So it's this angle. So now it's highlighted as yellow. So we're measuring this angle here. Okay, and that's has a double bond. Now write this down, please. It's 120. So now the next one is how to determine the stereochemistry of this carbon. So you can generate it here, or you can also generate it in ChemDraw here. So I went back to ChemDraw. If you put the cursor in here, and then I can do object, show stereochemistry, and then it's an R. So you can also do that in Chem 3D. So now I want to determine the stereochemistry of this carbon over here. So how do we do that? So structure, detect stereochemistry. Shown at the bottom, the stereochemistry for C3 is R. So we're done with this part here. Okay, we are now going to build what is called a bicyclic structure. Now I'm going to build another molecule, which is now going to be the natural product pinene, although limonene is also a natural product. This was a presentation in our previous experiment. So if you isolate oranges, you will isolate limonene. That is the first molecule that we built. And then now we're going to build the other components that are co-extracted with limonene. So these are minor components or trace amounts. One is plus alpha pinene, the other one is minus alpha pinene. So the plus and the minus indicate the optical rotation. So we are going to build the minus alpha pinene. So now I have the cyclohexane again, and then we are going to make a double bond, and then there is a methyl in here, and then we are going to put, I'm going to use the wedged bond, okay. So there is a cyclohexane, 1, 2, 3, 4, 5, 6. There is an alkene, that's a double bond. However, there's another ring attached, which is a 4-membered ring, 1, 2, 3, 4. And in this carbon, there is a carbon or a methyl, okay? And then another methyl coming from here, from this carbon. This is now the structure of alpha pinene, and we would like to determine the stereochemistry of the chiral carbons. The carbon on top is achiral, sp2 carbon, achiral, sp2, achiral, sp3, but in this case it's achiral, achiral. We have two chiral carbons, this carbon and this carbon. So we can highlight the carbon here and then determine the stereochemistry on object and then show stereochemistry. So that's S. And then this carbon, highlighted, and then on object, show stereochemistry, it's S. So we would like to determine if we can also determine the same thing, chirality or the RNS configuration of these two carbons using Chem 3D. So I'm going to use again the lasso, and now I can copy, and then I will go back to Chem 3D and then paste. This is now the structure in Chem 3D, and then I can also change on view, model display, display mode, and sticks. Rotate the molecule to view better, and then on structure, detect stereochemistry. So it's showing you behind C1 and then C3. So at the bottom here, C1, C3, S, S. So this is the top, this is coming towards you, this carbon, these are the methyl, and this is the other methyl, and this is the double bond in here. So I'm going to you're going to draw this sideways, but now I want to eliminate the H's so you can see better. So to eliminate the H's, I'm going to use the eraser. So that's the eraser. And then I can erase the H's, so we're just looking at the skeletal structure of the bicyclic molecule. So now only the carbons without the H's. And we can now rotate the molecule so we can view it sideways. So this carbon, if I hover the mouse here, this is the double bond. This is the alkene, has a double bond in here. So it's flat. And as you can see, it's not entirely a chair, okay? It looks more like a half boat or like an envelope kind of structure because of the cyclobutane in the bicyclic structure of this molecule. And also this is a double bond. So this is a fused ring structure, and this is the methyl coming up. So in the question, the last question is draw the side view or sideways. So the last question, draw the side view. So you're gonna draw it in here, and then you're gonna draw it side view or sideways this way. This is viewing it on top. So this is actually protruding, coming up towards you, and this is on the plane of the paper. However, in the side view, which is this, you are looking at it this way, while this one now is on the side. So it's like the peak, and then this is the side. So you're gonna draw it this way. Part C of the worksheet. You are going to draw the mirror image and assign RNS designation of the given molecule. So for example, for structure number 1, the configuration of this molecule is R. So you're going to write here R, and then draw the mirror image. For this example, the mirror image is as a reflection in a mirror. So the H on top, methyl on the left goes to the right, Br on the left goes to the right, and then ethyl on the right goes to the left. So that's the mirror image of this structure. The other way to draw the mirror image of this structure is to retain methyl and Br on the left, and then switch the position of the H and ethyl. So ethyl goes on top, H to the bottom or to the right. You're going to do the same thing for numbers 2, 3, and 4. Determine the configuration of this structure. Write it here. The same thing for this. Write it here and write it here. And then draw the mirror image for the given structure. Next, part D. You're going to identify and mark all the chiral centers for the given structure. So, first structure, no chiral carbon, 0. For the next one, there is a chiral carbon, this carbon and that carbon. So 2 chiral carbons. So mark that with an asterisk, this carbon and that carbon. So it should show like this. Mark it with a star or an asterisk, the 2 carbons that are chiral. So for number 3 and number 4, you are going to do the same thing. Determine the chiral carbons, mark with an asterisk, and then write the number of chiral carbons in the given structure. For part E, you are going to name the molecules with the correct stereochemical designation. So for this example, this has 10 carbons. So number 4 carbon and number 6 carbon. Number 4 contains an ethyl, number 6 a methyl, and then number 4 carbon is R, number 6 carbon is also R. Example number 2, write the IUPAC name and then the stereochemical designation of the chiral carbons. For part F, you are going to identify the relationship of the given pairs of molecules. So for number 1, these are trans and cis isomers, and these are diastereomers. Now, you are going to do the same thing for example number 2 and number 3, and then you are going to identify whether the pair of molecules are either enantiomers, diastereomers, identical, meso, constitutional, or configurational isomers. For part G, you are going to identify the relationship of the structures given in the table and compare that with the structure, which is the erythros. So this chiral carbon and that chiral carbon, this is R configuration. This one is also an R configuration. So this is now that structure. It has an R and R configuration. So now determine the relationship between this structure and this erythros. You are looking at a Newman projection, and in fact you are viewing it sideways. So if you draw the Newman projection, this COH is going to be on top. So you're in between the H and OH. Now the H is on your left, OH is on your right, and if you're projecting this way, so now the back H is on the right, OH is on the left, and then CH2OH, anti or opposite to the C double bond OH. So this group and that group is going to be up, below. So the OH and H on the dashed wedge are going to be on the left side, while the H and OH on the wedges are going to be on the right side. In fact, these are the same, therefore these two are identical. So the next 4 examples, you are going to determine the relationship between this structure and that structure. And then the same thing, the structure and with the erythros. And then the same thing for number 4 and number 5. So that's the end of this experiment.